Welcome to the pre-recording of Lecture 6 of MCS 481 on computational geometry. In this lecture, we open up the third chapter in the textbook and start studying triangulations. The motivating or kind of the introductory example to thinking about triangulation is the Watchman problem. You have an art gallery. How many cameras do you need to guard the gallery? So this is solved. It's called the Art Gallery Theorem. And the purpose of this lecture is to go through the proof using concepts that we have introduced throughout the course already. So this is after the second week. The course could also be seen as constructing an algorithm for placing the cameras. Assuming that instead of the art gallery, a very peaceful environment, your floor plan could be something that should be guarded, but it's actually quite dangerous to place the cameras. So you want to give very precise instructions on where to place these cameras. So that is a problem that we will solve as well. All right. What is now the Watchman problem? So here it is. So we have a floor plan, and the floor plan is a polygon. So we have worked with convex polygons, but to allow for general floor plans, our polygons do not need to be convex. Now, they should not have holes in them. Holes that might be important later on. Holes, they are vertices inside the polygon or inside edges. So in mathematics, it's very important that we have clear definitions. So the simple polygons is important. So it's a simple word, but it is important. So then in 1975, the Art Gallery Theorem was proven. So if you have n corners of your floor plan, then n over 3 cameras suffice. So now n over 3 may not always be an integer number, and you cannot have half cameras. So it suffices that you take the floor. If you have 7, then you're good enough with 2 cameras. We will see that convex polygons may need fewer cameras. So the floor of n over 3, so the floor is the highest integer that it comes close to the number n over 3. So we will see that, and as an exercise, you will construct examples where you need fewer cameras. So there is the proof. So the theorem was first proven in 75, but there was a book proof, a proof from the book that follows the 1978 proof by Fisk. Finding really the minimal number of cameras that you need is not considered here. So that is an NP-hard problem. So we will see that the algorithm that we construct will also actually be efficient. NP-hard might mean that there is not an efficient algorithm for it. All right, let's look at the worst cases. So let's look at some floor plans to get somehow an understanding of the statement of the theorem. So here we have a floor plan, so 2 floor plans that are comb-shaped. So if you still have hair on your head, you use a comb. So with 6 vertices, you will need 2 cameras, 6 divided by 3. With 9 vertices, you will need 3 cameras. So let's look at these floor plans first, and let's try to solve it. So somehow you may want to think, wait, if the room is just a triangle, so 3 vertices, 3 divided by 3 is 1, so 1 camera is needed. Fine. I should actually have said this as the first case. These are more special cases. How do you solve this? Well, we introduce triangulations. So if we triangulate, and there are many ways how to triangulate, we consider a triangulation. Then we can determine by coloring where to place the cameras and how many cameras that we will be needing. So, what does this mean? It means that it suffices. Now, here is where this is. So, there are two concepts that are introduced here. So, there is the concept of a triangulation. So, the polygon is now seen as a collection of triangles. Triangles that do not overlap. And the union of all the triangles is the entire floor plan. So again, definitions are important. I'm just illustrating a triangulation. Now, why does the coloring solve this problem? Well, look at the green dots first. If you have a camera here and a camera there, then you can actually guard the entire art gallery. So there are regions that are seen by both cameras, but the triangulation ensures that every point inside the triangle is watched, is guarded. Okay, so the different colors mean that vertices, corners that are connected by an edge, they receive different colors. So in a triangle, you need at least 3 different colors, but we will see that there is a systematic way how to assign colors so that every adjacent, so here we have a red triangle here, a red vertex, and you see that all the adjacent vertices, they do have different colors. Okay, so that's actually the idea of the proof. Let me now indicate why the holes were important. I'm going to make now a polygon that has a hole. It's actually not a hole, but it has an inner vertex, and it has 3 inner edges. And now you see that you cannot get away with 3 different colors to make sure that adjacent vertices are receiving different colors. So this is an example of a floor plan that we don't want. This is where understanding what is simple is so important. So this is what we do not want. Okay. All right, I said that this was the idea of the proof, but remember we are interested in the number of cameras that we need. And if you understand how to triangulate and to color, you can actually solve this problem now for any given floor plan by hand. But we want to prove that for n corners, you may need n over 3 cameras. So here we actually see this. So we have 6 corners and we need 2 cameras. here is the idea of the proof now. So we have a polygonal floor plan. We triangulate the floor plan and then we assign colors. And you have choice here. So there is also choice on the to triangulate. There is also choice on whether you like the green cameras, the red ones, or the blue ones. But you have to pick your color, your favorite color, and this is where you place your cameras. And by inspection, we see that every spot on everything of the floor plan will be guarded. All right, we understand the problem. Here is a case where all the edges are either vertical or horizontal. This is where you have in buildings that were designed in a very, not in a medieval fashion or in a kind of artistic way, but they were done in a very systematic way. All the walls are either are perpendicular to each other or parallel to each other. If you have that situation, then actually you can work with the rectangles. So if you have a rectangle, and here I'm drawing a rectangle, you can see that one single camera will suffice. So draw examples. So to justify that that many cameras suffice. In some sense, a more ambitious exercise is to also essentially redo the proof that we're going to do, but then doing this with rectangular floor plans, where your triangulations are actually rectangulations. So that's a more ambitious exercise. Here the point is it's kind of open a little bit, but draw examples just that you see enough for the algorithm, so that you can also do the coloring and indeed see that you can get by with n over 4. So draw 8 corners, 16, etc. It's also, it could in fact be, if your floor plan is like this, then, and if you have cameras that can turn uh, around enough, then one camera might even be sufficient. Okay, um, the number of cameras, n over 3, the floor of n over 3. Now, how many triangles are there in a triangulation? Because that actually solves it. With every triangle, we have 3 different colors, 3 different positions on where to place the camera. So if we know the number of triangles, then actually we divide that by 3. So that's how the idea, how it links the coloring to the triangles. All right, the number of edges and the number of vertices equals the same in a convex polygon. In a convex polygon, the number of triangles is also very straightforward to determine. So here you see the algorithm to actually make a triangulation. So you pick one vertex, any vertex, and then you run, so you go to the nearest adjacent vertex. You have 2 vertices, and then the vertex that is adjacent to that. So notice that when we talked about triangulations, convex hulls, we were having the edges seen as vectors. So you can actually walk very quickly around clockwise, counterclockwise, depending on what you picked. But you can see that this theorem here is very straightforward for convex polygons. So for convex polygons, we actually have that any triangulation, or there is a triangulation that has n minus 2 triangles. Now again, simple polygons may not be convex. So it's a little bit harder. Okay, as mathematicians, what do? We try to reduce it to the case of convex polygons. Okay, so we also use established proof techniques. So we know that this also holds for polygons that have three vertices. These are just triangles. So we know already that one triangle, just one triangle in the triangulation. So that is the base case. That's what we can solve. Okay, now we will apply our proof technique. So we assume that the theorem is true if you have polygons with n minus 1 vertices. It has been proven for any polygon up to n minus 1. So then we're going to say, well, wait, if we look at the leftmost highest vertex, we will reduce this to the case of n minus 1 vertices, and then apply the induction hypothesis. So the induction hypothesis will work on a polygon with n minus 1 vertices. It's true for n minus 1, so we can already say we have n minus 3 triangulations. And now we know how many more triangles that we can have. That's only one more. So here is where the correct application of the induction hypothesis is important. So proof by induction, if there is a base case that is simple, we state it. But then we need to actually say what is the induction hypothesis. So for any polygon with k vertices. And we need to show, and that's what's going to happen now, we have to apply the induction hypothesis. Okay, so there is a character that's important here, that's that V. So let's look at that vertex V. So we have two cases. We have already seen that convex polygons are easy. So we have a quadrilateral, P, and we will consider two cases. Now you may look and shift a little bit uneasy. Wait, you're doing this for quadrilaterals and for 4 vertices. So P, U, V, W, and one unnamed vertex. But that anonymous vertex is actually the one that is makes the distinction here. So we don't know anything about that anonymous vertex, and it could be many vertices of that. But here, for our purpose, so it matters whether the line segment U and V, and actually you can see the idea of the proof already. The left case is actually easy. So if UW, that line segment lies entirely inside the polygon, then we're done. Because then we can separate V from all the rest. So in some sense, if you are too quick in proving, you may think that you're done. And that would already give you a lot of credit, but actually there's more work to be done to resolve this case here, where that anonymous vertex, we didn't give it a name, makes that the UW actually does not lie entirely in the polygon, and you cannot use this. So let me again, this is something that is forbidden. So this is not a separation, a cut that we want to make. So we will focus on that case now. All right. So I actually said in words, I gave the proof for the first case. So here is actually the proof written in sentences suitable for slides. So consider the setup. It's important, the V is important. If there is a V, a vertex, it has two adjacent vertices. These are U and W. So this is a proof by picture. In the proof in words, if you don't want to see the pictures, you have to say that it's actually implied by the triangle, but you picked the leftmost vertex in your polygon. U and W are in the orientation, so I'm now working counterclockwise, but in the orientation, the alphabetical order here too, U, V, W, U is adjacent to V, comes before, and W comes after. So that is what it means, consider the triangle. Because the line segment lies entirely inside the polygon, I have a valid triangulation or subdivision when I'm when I'm cutting along. And that is actually also proving, so here we have the induction hypothesis applied. The polygon minus, so the polygon here is a triangle, but there is also the famous statement without loss of generality. So without loss of generality, so you can think of this polygon now something that is entirely something else. So you can then arrive at the desired result. Okay, but we still have more work to do. What about the case when the line segment does not entirely lie inside the polygon? Okay, if that is the case, then there is, so now it's time to give that pesky anonymous vertex a name. There is a vertex that is actually farthest to the left of UW, and it's not V, so that's important. So there is such a vertex here. So in some sense, I was drawing a quadrilateral, not convex, concave, and this choice was made so to get to this notion of the vertex, that it is a vertex of the polygon. You can also reason, why does this V prime exist? Well, if it doesn't exist, then UW must lie in the polygon. Or if that VW V prime would correspond with V, then you wouldn't have a polygon anymore. So that is important. You would have not a simple polygon anymore. You would have a hole. The hole would be that entire triangle. Okay, we can't use UW to separate, but can we use the segment V prime? And yes, that's where the definition of V implies that VV prime lies entirely inside the polygon. And that can be used in a triangulation. Okay, does that prove it? On the quadrilateral, yes, it does. So you see, we have 4 points, and we now have a triangulation with 2 triangles. Okay, let's write this up now. So we will apply the induction hypothesis without explicitly saying that we are using this quadrilateral. We have the property that the edge VV prime lies entirely inside the polygon, and it is splitting, therefore, the polygon into pieces. So it has actually separated V from the rest of the polygon. So that's actually what we want. So the 2 remaining polygons, they have 1 vertex left. Okay, now it's important to do the count. So we have the 2 pieces. that have one and two vertex, but we have to be careful that the v prime, so again this was the anonymous vertex that caused problems, the v prime, we shouldn't count it twice. The sum of the two numbers of vertices of P1 and P2 actually does do the count of V prime and V. Okay. So we are interested in the total number of triangles. So that's actually the point. In making the sum of the number of triangles, we apply the induction hypothesis twice, once to P1, once to P2. We know how many triangles there are, we add them up, and then we replace the M plus M1 plus M2 by N plus 2, and that gives us the statement of the theorem. Quod erat demonstrandum. Okay, we are through. Still 10 slides to go, but this was probably the first difficulty and a very important property of triangulation. So if you're going to construct a triangulation, any triangulation, then the number of triangles is linear in the number of vertices. That's also the reason why we carefully spell out this theorem. Colorings. So it's actually, we're almost through, actually not. So the second ingredient was to color the vertices in the triangulation. So a tree coloring, so let's now formally define it. So a tree coloring assigns different colors to adjacent vertices. Okay, and in this course, this is a course about algorithms, if you're in the theory track or on the computational track. So we are not, so the existence is sufficient for math, but for us, we actually want an algorithm. We give this off to a computer and the computer will solve the problem for us. We do not want to do this by hand if there are a million corners of our floor plan. So the answer is, of course, in the affirmative, yes. Okay, so let's introduce the algorithm. So given a triangulation, so that's the given. So in the next lectures we will go into methods to constructing triangulations. So given a triangulation, we have to visit all the triangles. So here, suggestively, I tried to show the floor plan of an art gallery, and it's also, you want to visit all triangles only once. So you want to visit the gallery and determine a path through all the rooms in the gallery. So that is also a practical application for robot motion planning, by the way. A problem that we will come back to later. So here is the notion. Every convex polygon is a graph of vertices, just a simple circle going both forward or backward. If you have a triangulation, you can define the dual of the triangulation. So you can identify with every triangle a vertex, and with every two adjacent triangles you have an edge. So the duality is that the triangles become vertices, and what connects the triangles now are the edges that are connectable. So here I drew the dual graph. Again, this is a picture definition. A picture definition that will be sufficient for the algorithm. All right. The fact that the polygon is simple uh, will make that there is a way to traverse the graph. So in depth first order. So you start here at the left and you walk through. So we walk through the, oops, sorry. Uh, I give away too much of the solution. So here you see we go clockwise. Clockwise, the numbers give us the label. So the dual graph is a graph, um, but uh, the fact that it is a simple polygon makes that there is a very nice way to traverse this. So depth first means that you have to go here to 8, 7, 9. So there is the left and the right turn that you make. All right, so this orders the vertices. So you can traverse, it orders the triangles. So every triangle has now a unique order. So, and you can apply the tree coloring. And there is now a systematic way of doing this. Once you have chosen your first two colors, you take your first two favorite colors, then everything is determined. So I hope that this is probably somehow the easiest way to see. Red, blue, green. So then actually you have no choice left for the other ones. I mean, you cannot put blue there. So this will be a red one, this will be a blue one, this will be a red one. So there is now a unique way to do the coloring. So you have an algorithm to solve this. Okay, two exercises. So in the previous lectures, we introduced data structures to store subdivisions. So we used the doubly connected edge list for this. Here apply this in exercise 2. So write pseudocode to actually visit all the triangles in depth first order. So I was stumbling a little bit at the slide where I mentioned the depth first search order in the graph. Any graph admits a depth first search order. So this goes back again to data structures. So in some sense, exercise 2 uh, is necessary for the algorithm. Exercise 3 is then the second step. So given again a data structure that stores the triangulation and the tree coloring of the first triangle, write now pseudocode to apply a tree coloring to all the vertices. So if you have the first triangle colored, then you have also actually the second triangle, the adjacent triangle colored, except for the edge that is not shared. So that's also the argument that I was going over too quickly, that after the first triangle, everything is fixed. So write pseudocode to do this. If you write pseudocode, you have to specify everything except for the primitives. So you can And you should also use the operations that you can do on the doubly connected edge list. All right, now comes the end. So the Art Gallery Theorem. So the proof is essentially quite short. So I gave the bottom-up approach. The main uh, goal in the proof was actually to prove the first statement. So any simple polygon has a triangulation with n minus 2 triangles. We define the dual graph of a triangulation. So it says here the two sentences, sentences 2 and 3 in this proof define what is the dual graph. So it's important to observe that as the polygon has no holes, there are no loops. So again, I gave a counterexample of a simple polygon that actually will make a loop. So if you have the dual graph, there is actually you can traverse everything. The dual graph can be mapped into a tree. And a tree we can traverse in depth first search order. Again, data structures. As we are traversing, we can now apply the tree coloring. And actually, any color that you pick is fine, but apparently it's important to pick the least number. So I glossed it over. So you pick, of course, the color that was appearing the least number of times. And that number is less or equal than n over 3. And that finishes the proof. So it might be good to go through the slides which are posted at the course website. It might be good to go through them now backwards, and you could start from here and write out the proof. So actually the first line is actually the important statement that we proved about triangulations of simple polygons. All right, this is an exercise with a proof from the book. Write out the solutions to the exercises 1, 2, and 3. We are looking backward to the previous chapter where we introduced data structures to store subdivisions, the doubly connected edge list. The purpose of the book is also, the purpose of the course is also, and the lectures, is that you will have better access to understanding the textbook and understanding the exercises. This is the end of the second week of classes, and I hope that until now we have somehow given a good overview of what computational geometry is.